So our next speaker is François Malgouyres. He's from University of Sabatier, and the new, especially the new AI center there, the ANITI. Today he will tell us about a stable recovery of deep structured linear networks under sparsity constraints. Please.
So I will first describe the. Oops. Okay. So I will first give the statement without any technical details. So I first consider a family of function fw, which depends on parameters w. You can think of a neural network. And then I have learning sample, which are xi, yi. So what I'm looking for is a condition that is sufficient to guarantee the stability property. And in practice, since I want this condition to be sharp, I will look for a necessary and sufficient condition. The stability property takes this form. There exists C such that whatever W and W prime, if the empirical risk at W is smaller than eta, and if the empirical risk at W prime is smaller than eta 2, then I am sure that the distance between W and W prime is smaller than C times eta. And therefore, when eta becomes small, I am sure that W and W prime are close to each other. So we do care about this stability property because first, it provides a way to guarantee that the features in the latent space and the output space are stably defined. For instance, if W and W prime are both provided by different algorithm, or if they are provided by a different run of the same stochastic algorithm, then I know that W prime, if they both manage to lead to a small empirical risk, then I know that W prime and W are close to each other, and therefore FW prime and FW are also close to each other. And even the latent space are close to each other and therefore can be interpreted and so on and so forth. The second advantage of this stability property is that if I know by another research or another analysis that there exists some W that generates the data, for instance, I might know it because I know that the underlying phenomenon is smooth, and I know that there exists a neural network that can approximate this kind of smoothness, then I can control the risk. The risk, indeed, if I have this W, then I know that the risk for this W is small, and I also know that the empirical risk is small for this W. If I have an optimization algorithm that managed to find some W prime such that this quantity is small, then I know that W prime is close to W, therefore FW prime is close to FW, and therefore the risk of W prime is close to the risk of W and is therefore small. Okay, so that's typically the kind of reasoning that was made in compressed sensing where this whole stability property and kind of analysis come from. In order to describe this statement, I need to describe the family of function, the condition, and I will not have time to describe it in detail, and state the final result. So concerning the family of function, we consider a neural network of a depth h. There are h-1 hidden layer, and the size of the layers are m0, etc., mh. I write mh equal m, and I assume that the transform between any two successive layers is defined by capital S parameters. And the transform between two layers is defined by this kind of matrix, the matrix mh of w. So from the layer h-1 to the layer h, I have this matrix. And this matrix is defined with these parameters. Okay, so if you think of a fully connected feed-forward neural network, you just take the entries in W and write them in this matrix. If you think of a convolutional layer, you take these parameters, you construct a top-lex matrix, and then you concatenate several top-lex matrices depending on the architecture of the convolutional layer. You can also take into account locally the action of a ReLU activation function by just canceling some lines in this matrix. Okay, so that's what we call structured linear network. And the function defined by the network take x and multiply it by m1w1 and so on, etc., etc. So when compared to the neural network that are actually used in applications, we don't have any bias and we don't have the activation function. What we do have is a sparsity model. We have a model here that contains several sparsity patterns or supports. And we assume that we know it. So we have a constraint on the weights W, which belongs to this set, but there is also an M here, which is here to indicate that there exists some support in the model, so that the support of W is included in S, which means that whatever H, the support of WH is included in SH. So for instance, you might think of a S prime sparse support. That's probably the most standard idea one might have. There are a few notations here. NK is this set. W contains all the weights. WH, just the weights that are used to define the transform between the layer H-1 and the layer H. And this is just 1 and 3. Okay, I have this set in which I just removed the W such that there exists one WH which is equal to 0. And on this set, I have equivalence relationship which corresponds to the rescaling between the different layers. So I say that W is equivalent to W prime if there exists some rescaling parameter, lambda H, whose product is equal to 1, and such that I can obtain WH by just multiplying W prime H by lambda H. And then I say that W prime belongs to the class of W. Okay, so this class of W is some kind of hyperbola manifold. Of course, if W prime belongs to the class of W, then when I look at this product, I can take the lambda H out of the M, and since their product is equal to 1, I have this equality. And therefore, whatever X, I have FW of X equal FW prime of X. And therefore, there's no way I can distinguish any element in this class. And my metric needs to take that into account. So I have a metric which is between equivalence class. Okay, I won't get into these details. To check that it's relevant and to check the detail, please go see the reference. Okay, now I'm going to talk about tensors. So we consider order H tensors, so there are H axes, and every axis is of size capital S. I denote the tensor space with this notation. One tensor entry is indexed by H index, or one bold index. And I will consider rank 1 tensor. I say that the tensor T is of rank 1, and I denote T belongs to sigma 1. If and only if there exists W such that Ti is equal to the outer product of W1, etc., WH. Okay, for matrices, for instance, you recover rank 1 matrices. And we have the Segre embedding, which is a very important character in this story, which is a way to parameterize sigma 1 by just taking weights and computing the outer product between W1 and W2, etc., WH. So P is nonlinear. Okay, it has many properties, and actually understanding P is a key issue in this theory. We of course have identifiability. If W prime still belongs to the class of W, P of W prime is equal to P of W. That's well known. And what we established in this paper is that actually, if P of W prime is close to P of W, then the class of W prime will be close to the class of W. Again, there are details and constants which are provided in this paper. Why do we care about tensors? It is because we have this tensorial lifting property. Whatever M1, MH, the architecture of the network, whatever X, the input samples, we know that there exists a unique linear map A that goes from the tensor space into the output space, such that for all W's, the application of the network to all these inputs is equal to A, P of W. And so here we have something complex that depends on the architecture, on the samples. And here we have something which is much more simpler because we just have something nonlinear, P, okay, but we only have to understand it once. And then we have A, which is something linear. And so everything and all the properties of the landscape of this function, and in particular, the kind of property we are after, the stability property we are after, will depend on the geometry and on the connection between the geometry of A, so its kernel, its singular values, its range, etc., and sigma 1 and sigma 2, the rank 2 tensor. So we have exploited this to establish a sparse deep null space properties. So I won't get into the details, it's too technical and I won't have time. But if you look on the drawing, we have one manifold here, one set, which depends on the Séguin embedding P. And the property says that it intersects this set, which depends mostly on the kernel of A, and the intersection, they intersect at 0, and roughly speaking, the intersection must be transverse, okay? We call this property sparse deep null space property, and we will see that this property is both necessary and sufficient to guarantee the stability. Okay, we obtain these two theorems. Assume that M1, MH, X are such that A satisfies the deep null space property. Then, if W and W prime are such that the risk is smaller than delta and eta, if eta plus delta is smaller than rho, then using traditional compressed sensing kind of proof, we have that P of W prime and P of W is smaller than this. And if we have the stability, if we add the stability property I announced about P, I obtain that the distance between the class of W prime and the class of W is smaller than, again, this quantity where I have here my empirical error. And the sufficient condition is necessary. If we have the stability property, then A satisfies the deep null space property, and I can provide the constant here. Okay, thank you for your attention. You can find details and application to convolutional linear network in the paper, which are available on the web. Thank you.
Okay, thanks. Yeah, we have some time for a quick question. So there was a question on how easy it is to check the deep null space property in practice, and are they guaranteed with high probability for random choices?
In general, I can't tell. In fact, you have to redo the analysis for every architecture you have. So maybe if we do this exercise several times, we'll end up with good ideas to speed up and to have an intuition, a quick intuition on everything. But in general, you need to redo the analysis. There are some kind of this I didn't have time to present it, but I skip it. But you might also obtain sufficient condition to obtain the deep null space property, and this condition might be much more easier to check for one given model. For instance, here we easily obtain some sample complexity, assuming A is sufficiently random, for instance. So in many cases, you can do an analysis. Okay, but you have to redo it all the time.
Okay, there was a question for François. So could you give an example of a system satisfying your conditions? I suppose it is the null space property conditions. So.
Okay, do you hear me?
Yes.
So we have actually been able in the paper to calculate everything by hand and to provide all the clues to make the calculations for convolutional neural network. And for convolutional network, we end up with a condition that we can easily calculate with an algorithm which has a reasonable complexity, which is of small complexity. And basically, I don't know much beyond that, but I'm sure there are plenty of open questions in that direction.
Oh, sorry, I'm muting myself. Okay. And also, is there analog? I mean, that's a related question, I guess. Is there analog of a mutual coherence condition from compressed sensing as a easy to verify sufficient conditions for the deep NSP?
I would basically do the same response. The difficulty here is that we do not know so the analog of the linear operator on which we we look for a mutual incoherence property. We don't know this A explicitly. We only know it implicitly, and it depends on the network and on X, etc., etc. So calculating something like the mutual incoherence might be difficult. I have not tried it. But again, the difficulty is that this matrix A, or this operator A, is only partially known. But we don't, in practice, we need to calculate its kernel, the smallest non-zero singular value, and then there is this deep null space property, which is often verified as soon as the kernel is not too large. Actually, there are intersections between manifolds, and if the two manifolds are small, in general, the condition will be satisfied.
I think it's more open-ended. Like, can you discuss more the role of initialization in your results? So maybe you can take turns to say something about it.
Looked at the optimization problem. So the property we studied was mostly related to the bottom of the landscape of the objective function. We say that at the bottom we have something which is compact or small in some way, so that any solution, any weight in the bottom of the landscape of the objective function, they will be close to each other. But we need not study how to get there, and in particular how to initialize an algorithm and what is the landscape of the objective function, and if the landscape is favorable in a way and makes it possible to reach this bottom.
So if I may add, like in practice for these type of problems, if you say doing a random initialization, what do you usually observe? Like, do they converge to the minimum, or are they stuck at some other points?
You're asking me a question?
Yes, I'm asking you because you're saying that.
Well, actually, I don't know. In general, in theory, you get to a critical point. In general, you can also even expect to get a second order critical point. But then the question whether these critical points are low and correspond to low critical values really depends on the architecture of the network and on many ingredients. But you have to study to redo the analysis every time.
Okay, thanks. Yeah, so I just remind everyone that the conference has a Slack workspace, and you can, if you have more questions offline or come up with any ideas, you can communicate with the papers and speakers there. Actually, I've seen already some posted questions there in the channel for today's talk. And also for the speakers, please do join the Slack workspace, and that's a great platform to interact with, for the conference. And while the conference is virtual, we do hope these mechanisms can make it more valuable. Okay.